This video is Kinetics 6, our last one for Kinetics, and this is going to be about the temperature dependence of the rate constant. And we'll go back and look at some mechanisms. We're going to look at transition state theory as an explanation for the result that the rate constant depends on T. First, we're going to start, though, with some empirical evidence, some experimental work that was done by Arrhenius, A-R-R-H-E-N, that's an H, I-U-S. Let me do that again. Arrhenius, A-R-R-H-E-N-I-U-S, equation. And Arrhenius was a very early chemist back in the late 1800s or so, and he knew that the rate of the reaction increased as he increased the temperature of his reacting system. And so he came up with an equation just kind of based on his experiments. And so kind of a general rule that we know today about reactions, I'll say from experiment, the general rule is that the rate of the reaction doubles for every 10-degree rise in temperature, approximately. So the rate of the reaction approximately doubles for approximately every 10-degree C rise in temperature. Okay, not all reactions are the same, but it's just kind of a general rule there. So the equation that Arrhenius derived, is K is equal to A e to the minus B over T. This was kind of the original form of his equation. A would be called the Arrhenius A constant here. Nowadays we know it to be the frequency factor having something to do with molecular collisions. It's a constant for each reaction. B has to do with the activation energy we know today. Back then it was just a constant. And then in time, his equation evolved to e to the minus EA divided by RT, so that would mean B would be equal to EA over R. And for this, excuse me, the EA is the activation energy needed to get the reaction started. And R is the gas constant, the ideal gas constant, which is going to be 8.314 joules per mole per Kelvin. All right, so then we're going to just kind of look at this equation and learn how to do calculations. If you know something about the activation energy, for example, you can predict a new rate constant associated with a new temperature. And by the way, I think I've been using the word rate. What I mean to say is the rate constant. So let me talk about that. We know that the rate of the reaction increases with temperature. Why would that be? Because the rate is equal to K times the concentration of whatever your reactants are, raised to the powers M and N. So if the rate of the reaction is increasing with temperature, The reason why is because the rate constant is increasing with temperature, and the Arrhenius equation is for the rate constant, not necessarily the rate itself, although they're proportional. All right, I should have mentioned that. So now we want to just work with the equation. We have K is equal to A e to the minus EA over RT. If we take logs of both sides, we can do natural log here. The natural log of K would be equal to the natural log of A minus, because you're saying the log of e to the something, so here's the something right there. Okay, and so then we can rearrange this and say ln K is equal to negative EA over RT plus the natural log of A. All right, then if we wanted to go to base 10 log, we would say 2.303 base 10 logarithm K is equal to the natural log of K, and then negative EA over RT, and then plus 2.303 base 10 logarithm of A. Then we can divide both sides of the equation by 2.303, so we'll have base 10 log of K, negative EA over 2.303R. We'll separate here and say 1 over T, and then this would be plus the base 10 logarithm of A. You know, we're usually graphing this data, so the base 10 log is very convenient here. And if we were going to do an experiment, we would figure out the rate constant for a particular reaction as a function of temperature, and temperature in Kelvin, by the way. And then we'd have to take the logarithm of the K and then the inverse of the temperature and do a plot of logarithm of K versus 1 over T. So you can see it's got a negative slope because it's got a negative sign there. And we would find here that the slope equals negative EA over 2.303R. Okay, so we do an experiment. We calculate the slope from the data. We're interested in figuring out what the activation energy is for the reaction. It's a very important constant. So we would say then that the activation energy would be the negative of the slope, which is going to be negative anyway, times 2.303 times R, the 8.314. Okay, so that's just how you calculate the activation energy for this system. Okay, that one's fairly easy. Now, we don't always have information on the A constant, that frequency factor. So we use another form of the Arrhenius equation. It's called the two-point form or the two-point method. And that can be very useful, as you will see. So now we want to talk about the two-point method. And there's different forms of it. I actually have like about 4 or 5 different forms of it typed up. I'll see if I can remember to post that for you. But let's just go through just 1 or 2 of those forms now. I'll go back to black. So if we took the logarithm of the Arrhenius equation and we did it twice for 2 different data sets, we would have the logarithm of K2, rate constant 2, is equal to negative EA over R. Sorry, forgot my 2.303R there, and times 1 over T. And then you got plus the logarithm of A, and this would be T2 there. Okay. Then we could have a similar equation for T1 and K1, temperature 1 and rate constant 1, and that would be equal to negative EA over 2.303R, 1 over T1 plus logarithm of A. The next step here is to subtract the logs. And we're going to say logarithm K2 minus logarithm of K1 would be equal to negative EA over 2.303R times 1 over T2 minus 1 over T1. Log of A minus log of A is 0. Then we could continue here and say logarithm K2 over K1 is equal to negative EA over 2.303R, and that is 1 over T2 minus 1 over T1. All right, that is it. That is it right there. Now, I like this form because it comes straight out of the derivation. But different books are different. If you're going to Google this, you might find it slightly different. Another form would be the logarithm of K2 over K1 is equal to positive EA over 2.303R. And then this would be 1 over T1 minus 1 over T2. So in other words, we have the negative of this term in parentheses. So that's the negative of that. And then you'd have the negative of that. So, or else you could just say you factor this negative sign into this, and then it'll flip it as 1 over T1 minus 1 over T2. All right, so that's another form. And sometimes lots of books have that because it's positive. Okay, another form is when you take the you collect the T1 and the T2 together in the denominator, then this is going to be T2 minus T1. I'm sure you're familiar with that operation. So it'll be the logarithm of K2 over K1, and that would be EA over 2.303R, and this would be T2 minus T1 divided by T1 T2. And some people like this because this is delta T in the numerator. You just change the temperature, just subtract the temperatures, divide it by that number, T2 times T1. So, I don't know, people like that. So that's another form. And then another form here is flipping K1 and K2 in the argument of the log, and that could be any combination, I suppose. Make it red there. So if you said the logarithm of K1 over K2, go back to this equation in the red box. So if you flipped it, K1 over K2, that would make it positive 2.303R, and then it would be 1 over T2 minus 1 over T1. This is enough to make you crazy, right? And it depends on what you're looking at in the books. But I like this first one because it comes straight out of the derivation, and I'm happy with this one. But whatever form you choose to use, make sure your numbers are consistent. I like this first one because K2 is listed first, T2 is listed first, K1 is listed second, T1 is listed second. It just, the whole thing just makes sense to me. But then you got to remember to have that negative sign there, and students tend to not remember that. So be warned. All right, why do we care about all of this? So we'll look at an example here, and we'll use that first form. So you have the information, the rate constant, for HI formation, is the following. That's not worded very well. So you have a gas phase reaction of H2 and I2 forming 2HI in the gas phase. So that's your reaction. And you're given the data, K1 is 2.7 times 10 to the minus 4 molar to the minus 1 seconds to the minus 1 at T1 is equal to 600 Kelvin. Then you've got rate constant 2 is 3.5 times 10 to the minus 4 molar to the minus 1 second to the minus 1 at T2 equals 650 Kelvin. And our problem here is to find K3 at 700 Kelvin. All right, so let's put up our equation and think about this. So we can use a base 10 log here. Base 10 logarithm of K2 over K1 equals negative EA over 2.303R times 1 over T2 minus 1 over T1. And let's look at the details here. Okay, there's the number. All right, we're going to plug in the numbers, and we have the logarithm of 3.5 times 10 to the minus 3. Oh, I see there's a mistake up here. This should be a 3 right there. Sorry about that. Divided by 2.7, 10 to the minus 4 is equal to negative EA divided by 2.303 R times 1 over 650 Kelvin minus 1 over 600 Kelvin. And we can calculate the logarithm. I need to do this part right here, sorry. 3.5 E minus 3 divided by 2.7 E minus 4. That is equal to, so you have the logarithm of 12.963, and that'll be negative EA over 2.303 times 8.314. I'll put the units in a minute there. 1 over 650 Kelvin minus 1 over 600 Kelvin. Then take the logarithm of the left-hand side of the 12.96, and you get 1.1127. Let me double check that because that does not look right to me. Yep, 1.127. I think I'm trying to figure out what was wrong there. 1.127. Okay. All right, and then we've got negative EA. This number together, 2.303 times 8.314 is 19.14. The units for R are going to be joules per mole per Kelvin. You take 1 over 650, you subtract that from 1 over 600, and the answer here is going to be negative 0.000128. Lots of digits here. We'll truncate them very, very soon. And that is a negative number. So if you subtract 1 over large minus 1 over small, you're going to get a negative number. So this is, students get messed up here. This is divided by 1. And the EAs, the negatives are going to cancel. You're going to have EA is equal to 1.1127 times 19.14 joules per mole per Kelvin, and then you are dividing by 0.000128205. Okay, you're not multiplying, you're dividing. And I'm just going to check that again. Times 1.1127 0.27, and then divide by 0.000128. You get third, where'd it go? There it is. So you get EA 1.66 times 10 to the 5th joules per mole per Kelvin. All right, that's the activation energy. That is part one. You need the activation energy to do this second part. It's only a one-part calculation, you know, the way it's worded, but in fact there are two parts to it. You have to get your EA first. So then actually look back to what we have here. Let me point things out to you. What we're going to do for the next step, we're going to substitute T3 here and K3. You're looking for K3 at T3. We're going to leave K1 and T1 the same, and the activation energy that we just calculated, we're going to plug in here. And so the only unknown will be K3. So that would be the strategy there. All right, so, whoops, let's move it up. That's our next step. So it's going to be the logarithm of K3 over 2.7 times 10 to the minus 4. And then that'll be equal to negative EA, which we just figured out. Whoops. 1.66 times 10 to the 5th joules per mole. That's the energy unit. And then we're dividing by 2.303 and 8.314 joules per mole per Kelvin. That's a negative 1. Okay, and then multiplying times 1 over T3, which is 700 Kelvin, minus 1 over T1, which is 600 Kelvin. And if you go ahead and do all of that, this part right here ends up being positive 2.05. So we have the logarithm of K3, divided by 2.7, 10 to the minus 4. The units are molar to the minus 1. Kelvin to the minus 1. So now we're going to take the inverse log or the anti-log. 10 to the logarithm of the something is the something. So this is K3 over 2.7, 10 to the minus 4, molar to the minus 1, seconds to the minus 1. This is 10 to the positive 2.05. So you learn how to do that in your calculator. K3 then is equal to, this part right here is 112. You can calculate that. So K3 then will be equal to 112 times 2.7 times 10 to the minus 4, molar to the minus 1, seconds to the minus 1. And K3 is 3.0 times 10 to the minus 2, molar to the minus 1, seconds to the minus 1. Whoa, that's the answer. That's a long problem. Very typical test question. Now I just want to go back and ask if it makes sense. So, oh, so tiny. There it is right there. Okay, so 3.0 times 10 to the minus 2 is K3. Does that make sense? So at 700 Kelvin, does it make sense that the answer is 3 times 10 to the minus 2? So you're going from 600 to 650 to 700. The numbers here are 10 to the minus 4 to 10 to the minus 3, so they're getting larger. And the question is K3, is that larger? 3.0 times 10 to the minus 2 So the answer is yes. 10 to the minus 4, 10 to the minus 3, and this one ends up being 10 to the minus 2. So at least you've got some monotonic type of relationship there, and that is always good. Okay, so that's the end of that problem, and you need to practice that. There'll be a group activity on that one, and we could probably do that one online together if we need to. All right, then just some other comments here, just some more qualitative stuff, just to have a sense of how we think about reactions today. We use something called the transition state theory. And the activation energy that is a fundamental part of the Arrhenius equation plays into this transition state theory. So what is the activation energy, which is given the symbol EA by Arrhenius? That's what we want to look at here. And you can look at a graph here of energy versus what we call the reaction coordinate. And the reaction coordinate just means you start with the reactants, and as time goes by, there's all kinds of changes, and then you finally end up with the products. So you could say the reactants are on this side. What are all the steps that lead up to the formation of the product? And we're looking at the energetics of that process. So if you add up all of the energies associated with your reactants, so it could be A plus B, we'll just put R there for the reactants. All the energy, so that's the kinetic energy of motion, that translational energy. We can add in the vibrational energy, then the rotational energy, the electronic energy, all the energy associated with the reactants, and then it's got some numerical value. Okay, we draw a line across, and that would be for the reactants. Now, in the case of an exothermic reaction, the products are going to be down here. And, if it's like that, then you would think reactants would go to products very easily because it's a downhill process. The products have, the sum of all the energies in the products is less than that of the reactants. But it turns out usually that's not the case, that the reactions can just sit there without formation of the products, or it could be just a very slow process. And the way we explain it is in terms of this activation energy. It's like a hill that has to be climbed. So this is representing the energies associated with the reactants. If you heat it up, for example, your reactions are going to have more and more energy until finally they've got enough energy, or it could be at that temperature as well. But finally they got enough energy to get over the mountain, and then, of course, the product states will be like that as well. But, you might have to increase the temperature quite a bit in order to get over that mountain. So that mountain involves the activation energy, which is the difference in energy between the reactants and the top of that hill. And at the top of that hill, the activated complex is formed, also referred to as the transition state. And this is where, the bonds are starting to break in the reactants. The new ones are starting to form. That is a very high energy situation before the reactant bonds are completely broken and the product bonds are completely formed. So it's up at the top there. If this was A plus B, oftentimes you see the symbol AB for the activated complex, and then there's like this little dagger thing that indicates that it's highly excited or highly energized. And then finally AB will fall apart to make products. Okay, so that's the activated complex. Those exist very short periods of time, sometimes femtoseconds, sometimes picoseconds. It's formed and then it's gone. So you don't think you'd ever be able to actually study those things. But nowadays, and I'd say probably for the last 20 years, probably even more than that, maybe even 30 years, the technique of femtosecond pulsed spectroscopy became available. The professor was Ahmed Zewail, and he was an Egyptian scientist, and he is from was from Caltech. I think he's passed now. But actually knew him, yeah. And he won the Nobel Prize for this work. He was able to photograph, in a spectroscopic sense, take spectra on a time scale of femtoseconds. And he was the first one to do that. And it had to do with an iodine complex. And so in a femtosecond time scale, you could see the changes that were taking place right at the top of that hill. So that was pretty exciting work at the time. All right, so that's an example of an exothermic reaction. If you want to know the energy thermodynamically, it's this right here. So this is going to be delta H, the enthalpy change for the reaction. So it's just that energy minus that, or actually it's products minus reactants. And then the activation energy is this other thing. All right, then if we had an endothermic reaction, it would be similar, except the energy of the products would be higher. So reactants and products. The activation energy is from here to here. And the difference here would be delta H positive because it's endothermic. Above, it would have been negative exothermic. All right, so that's the idea. There's a little bit more information about EA. All right, so then the transition, what's the relationship between the Arrhenius equation and the transition state theory? So the transition state theory says that the rate constant K is the product of Z, P, and F. So there's three things to consider when we talk about the rate constant. So Z is called the collision frequency. P is the probability factor. And F is the energy. I'll just say consideration and give you the details here in just a second. Okay, so there's three parts to it. We want to quickly talk about each part. So Z then is the collision frequency. And this is going to, in kind of early physics, we just talk about the collision of hard spheres or billiard balls. So the hard sphere model is that the collisions are approximately 10 to the 9 collisions per second. So this would predict a 2% raise. In temperature, or I'm sorry, in rate. 2% rise in the rate for a 10-degree rise in temperature. And we know that not to be the case, that there's a doubling of the rate for every 10. So we would say we just can't consider molecules as hard spheres, just billiard balls bouncing off each other and reactions happening every time. We can't do that because lots of times when they collide, reactions do not occur. So this ended up being, we'll say wrong, but it's actually still part of the consideration, but we have to modify the model a little bit. The next is P, the probability factor. And in our second thermodynamics chapter, we will learn about entropy. This is related to the entropy of the system, and it has to do with the orientation of the molecules when they collide. So, for example, would NO plus Cl2 react if they came kind of head-on at each other? In other words, I'm saying if this one came up to the chlorine that way, we would say that there's no reaction here, that it actually has to be the nitrogen which orients itself with the chlorine, because the products of the reaction are ONCl plus Cl. So those are the products. So it can only be explained in terms of this orientation. If it happened to be flipped, there would be no reaction. So that is the probability factor. That's kind of a simple example there. You know, only half the time, half of the collisions end up in product, but again, it would be more complicated than that. It's not just left or right. Okay, anyway, so that would be something to consider. This would be the orientations of molecules. And then finally, the last one, which is F. F turns out to be e to the minus EA over RT. And this is the activation energy. Now we know something about it because I showed it to you, what it means in the graph. And it's kind of a complicated function because this is a 1 over T relationship. So as the temperature goes up, then the whole term goes down, but then you have a negative in here as well. And so it's going to end up, there's an exponential relationship, but as the temperature goes up, we're going to find out that the frequency increases. So you got 1 over T, and then you get the negative, so it's going to make it positive. And we find that there's an exponential term in there as well. So then, let's see. One thing known about temperatures and activation energies. We looked at this graph in the gases chapter last semester, and if you look at the number of molecules with a given energy versus, I gotta remember this, energy, I think it is. You could use velocity instead of energy to get something similar. You're gonna get, or you could put, I don't know, that's good enough, yeah. Okay, so you get a graph that looks like that. So you would say that a certain number, actually it's probably a little bit more like that. Okay, so then you would say, you know, molecules with this much energy, there's so many of them. Let me re-say that. There's so many of them that have this much energy. Another number of molecules might have this energy. Another number of molecules have this energy, and so on. All right, now if you change the temperature, so let's say you increase the temperature where T2 is going to be greater than K1, you're going to find the whole curve shifts to the right. And this is going to be associated with T2. This one is associated with T1. So we find that the molecules are moving faster when you increase the temperature. And if you remember, the top of the curve here had to do with the most probable speeds or energies, same here and here. So you'd say when the temperature increases, more of the molecules are traveling at faster speeds and hence have greater energy. All right, that's an important graph actually. Now put it all together and finish up this topic here. We have from the Arrhenius equation that K is equal to A e to the minus EA over RT. From transition state theory, we have that K is Z times P e to the minus EA over RT. And so if you compare them, you see that A is going to be equal to ZP. So A is equal to ZP. So if you experimentally determined this value of A, which you can do, then you can determine at least the product of Z and P, and then with some other calculations you can figure out what Z and P are. And then graphically you can solve for EA and it'll be the same with either model. All right, so that's kind of the end of that. And then finally here, we'll talk about catalysts very quickly. And catalysts, as you know, in biological systems, you have the enzyme and the substrate. So maybe there's some reaction of the substrate that does not work very quickly because of the activation energy issue. And it'll kind of swim up and position itself in some pocket or cavity for the enzyme. Not always that way. It could be the other way, that the enzyme's moving into the substrate. But anyway, when the two interact, so you have the enzyme and then the substrate, maybe something like that, where it kind of fits in there. And when it does, then it's easier for the reactant bonds to break because they're interacting with the enzyme now, and the activation energy gets lowered as a result of that, and the whole thing speeds up. And so we say that the catalyst, I'm getting tired here. No, I did not spell that right. The catalyst increases the rate of the reaction, and it actually has to do with the rate constant, because when the rate of the reaction increases, it's not because the concentrations are increasing, it's because the rate constant increases. And so that's the effect. If you had a energy diagram versus reaction coordinate, and maybe you had a system that looked like this, we know that the activation energy here is going to be defined by that. But now you throw a catalyst into the system, and we saw the example in the mechanisms where the catalyst, first you put it in, and you see it on the left-hand side of the reaction. And at the end of the reaction, of course, it's regenerated, so you see it on the right-hand side as well. So we know that the catalyst increases the rate of the reaction. In the particular reaction where I minus was the catalyst, right? There were two steps in that mechanism, and I think the first one was the slow step. You have to go back and look at that. So the effect of the catalyst is to lower the activation energy, but we saw an example that had two steps in the mechanism. So this, in the presence of the catalyst, then you have, I guess you could call it EA1 here, and then EA2. This is only in the presence of the catalyst. You got two activation energies. The fact that the first one is higher is saying that the rate of the first step is slower Slower than the second step. All right, and there's all kinds of catalysts here that we can look at. You know, nitrogenase, for example, converts nitrogen in the air into nitrogen in plants. Certain plants can do that themselves. Legumes, for example, can extract N2 from the air and convert it to nitrogen as fertilizer for the plants. Otherwise, you have to add fertilizer. We can use sucrase as an example of an enzyme that breaks the sucrose molecule into glucose and fructose. You have to read about this stuff. Amylase is in our saliva. That's going to break the starch down to glucose. Lipase is an enzyme that breaks fats down into free fatty acids. Protease is an enzyme that breaks down protein into amino acids. Lactase is an enzyme that breaks lactose down into glucose and galactose. And lactose, some people are intolerant to it or intolerant to lactose because they don't have the lactase enzyme. I'm one of those people. It's not fun. All right, and then also we can talk about, this is kind of the last topic here. Bear with me. So we can talk about homogeneous catalysts and heterogeneous catalysts. So the difference between them, homogeneous, every single part of the system is the same phase. And heterogeneous, at least one has a different phase. Sometimes the catalyst itself has a different phase. An example of a heterogeneous catalyst is platinum. And here's an example, 2 SO2s in the gas phase plus O2 in the gas phase is very slow to form 2 SO3 in the gas phase. Turns out if you add a platinum catalyst, then things go very quickly. And the idea here is that you've got these platinum atoms at the surface of your platinum material, and the O2 molecules kind of swim up to it, and it makes the O2 bond much easier to break because they start interacting with the platinum, and then the double bond will break more readily, and then it can react with SO2 to form SO3. So it's heterogeneous because platinum is a solid and the rest of the system is gas phase, so it's a different phase. And let's see. Okay, and then we'll look at fuel combustion and call it a day, call it a week. How about that? So this one is an interesting problem here. Fuel combustion. Start out looking at the heterogeneous part of it. So take some octane, that would be a component in gasoline. So we'll use C8H18 octane as an example for gasoline. It's a liquid, and you react it with O2 in the gas phase. So this is liquid, that's gas, and the first thing that's going to happen here is it's a typical combustion reaction where CO2 gas and H2O, which starts out as a gas and ends up as a liquid, The H2O is CO2 and H2O are formed. This is heterogeneous because you got liquid, gases, gas, liquid, so at least two different phases there. All right, it gets more interesting here. This is not balanced, so I'm not worried about that. The combustion reaction gets interfered with by nitrogen in the air. So in other words, this gasoline is being combusted, oxidized in your car engine, right? And there happens to be nitrogen from the air present. So it's not a pure 100% reaction. You can get side products here due to the reaction with nitrogen. So you put octane, O2, and then you get some N2 here, all in the gas phase. You're going to get CO2, CO, NO, nitric oxide, plus H2O. So you get nitrogen oxide compounds. That's just one of probably several that are formed. And so we don't want that nitrogen to form. We want to have a good clean combustion because you get the most energy out of this first reaction given. And so you want to add a catalyst. And back in the, I'm going to say 70s, catalytic converters were invented for this purpose, to catalyze this reaction and eliminate the NO product. So you add a catalyst, you have C8H18 again, plus O2, and in the presence of nitrogens from the air, and then the catalyst was either platinum, palladium, or here's vanadium oxide, and lo and behold, the nitrogen side reaction was suppressed. You get CO2 and water back again. It's a heterogeneous catalyst, so it's still a heterogeneous reaction. Now, it turns out that gasoline back in the 70s had lead in it, and so the catalyst gets poisoned by the lead, and now we use unleaded gas so that we can use our catalysts and improve our CO2 and H2O yield. All right, so, but another issue here is the NO, this nitric oxide right here. Even though we have a catalyst that gets rid of a lot of it, we still do get the NO as one of those products. And we don't want the NO product. Whoops, we don't want that NO product. So the question here is, why is NO bad? And here's what happens. Oxygen in the air reacts with NO, nitric oxide gas, being produced by our cars to form NO2 gas, and that is that brown, yucky color. Sometimes we look, maybe from the mountains, we look out over the air and we can see that kind of a brown color, and that's due to the nitrogen dioxide. The nitrogen dioxide here, in the presence of sunlight, we say E is equal to H nu. You may remember that from last semester. Otherwise, you just say energy from sunlight. Produces NO in the gas phase plus oxygen in the gas phase. In the next step, the oxygen in the gas phase reacts with O2 in the gas phase to form ozone. We don't want ozone either. It destroys our windshield wipers, among many other things. High concentration of ozone is toxic, and the weatherman sometimes will tell you when there's too much ozone in the air. You got to stay inside. You don't want it breathing it in and irritating your lungs like that. So if you add this all up, you've got NO in the gas phase plus 3/2 O2 in the gas phase forms ozone in the gas phase. And that's why you don't want NO, because it reacts with the oxygen in the air to form ozone. So ozone in the upper layer of the atmosphere is good. It prevents, radiation from the sun getting to us and doing damage. So it's good to have it there, but ozone in the lower atmosphere where we exist, you don't want it at high concentrations because it can do some damage there. Anyway, this is an example of a homogeneous reaction, homogeneous catalytic reaction. The catalyst NO is gas phase as well. All right. And I believe that we are done with kinetics. That was 6 lectures. I have to add up the minutes to figure out how many real lectures. Our classroom lectures are about 100 minutes, so this is equivalent to at least 2 full lectures, maybe even 2.5, something like that. All right, I hope you have a good break. We'll see you on the other side when we get back to online classes.